Welcome everyone to today's webinar with Sparc Technologies Managing Director Nick O'Loughlin. Nick will be taking us through a presentation covering the latest developments across Sparc Hydrogen and EcoSparc. Please note that all attendees are in listen mode only. If you have any questions, you can submit them via the chat function at the conclusion of the presentation. Now I'll hand it over to Nick to begin. Thanks, Nick.
Thanks, Simon, and nice to be with everyone here today. I'll run through a presentation in about 15 or 20 minutes, and then please ask questions through the functionality on the Zoom, and I can cover those at the end. So to kick off about Sparc Technologies, for those that don't know the business well, we really have two separate segments of the business. So we are a main shareholder, a key shareholder in Sparc Hydrogen, which is developing next generation green hydrogen production technology. So there's a lot of news around green hydrogen. At the moment, it's largely negative, and that's really been driven by issues with the costs of the incumbent process to produce green hydrogen, which is via electrolysis. Our process, which has been developed in partnership with Fortescue and the University of Adelaide, does not use electricity, and it does not use electrolyzers. So it's a completely separate track of producing green hydrogen, and it has really strong potential to drive low costs, which can really unlock the market. So we're really excited by that JV, and there's been some really interesting developments there more recently. On the other side of the business, we deal with graphene, and we make graphene-based additives. Our flagship additive is called EcoSparc, and that's an additive for the anti-corrosive coatings industry. So we've developed that additive over a number of years, and now we're really on the cusp of commercialization with some of the large global coatings producers who will use that additive to improve the performance or the longevity of the existing coatings on the market. And I can come to that soon. So again, we've had some really strong progress there recently, announced some trials with BHP Mitsubishi Alliance, Santos, South Australian Government, and 29 Metals over the past 6 months or so. In terms of our corporate setup, we announced today that we have Simon Kidston as our new non-executive chairman. So Simon was the founder of GenX Power, which was sold to J-Power about 12 months ago for over $1 billion EV. So he has really strong credentials in the space, and we're really excited to have him as non-exec chair, having joined the board in December last year. I'm the managing director, and then I have a strong team based with me here in Adelaide, in Kent Town. Now, I think Sparc, one of the things that is notable is that we do have the two segments of the business. So we're in hydrogen production technology, and we're in graphene. How we manage that, and I think we do it well, is largely having those R&D projects separately. We do all of the R&D on graphene here in Kent Town, and we have a facility here where we do that work. And then for hydrogen, it's all done at the University of Adelaide. So from managing the business perspective, it functions really nicely. It gives us some optionality as to the tech that we're developing into these different markets. But if I look at how we're valued against some of our peers in the hydrogen space and in the graphene space, I argue strongly that we are heavily undervalued. And I've listed what I feel like the key peers are, and I suggest that you do your own research as well. But on the hydrogen side, our closest peer is a company called Sun Hydrogen, which is based in the US. They are developing a similar direct solid hydrogen technology. It's not based on photocatalysis, but it's a similar process. They're at a similar stage of development as well, and they're capped at over 100 million US, approaching 150 US. So that's a really strong comparable for us. And then there's a number of others on the ASX, including those drilling for hydrogen or doing other hydrogen tech like Hazer. And again, we stack up really cheap against those. And then in the graphene space, most of those companies actually produce graphene. We differentiate ourselves from those companies by not being a producer of graphene, but by being a developer of graphene-based additives. And that's a key benefit that we hold, strategic benefit, and I'll come to that when we get to discussing EcoSparc. So firstly on Sparc Hydrogen, and the point I like to make up front is that hydrogen is an existing market. It's a significant market at that. 95 million tonnes per annum a year is used, and that is primarily for ammonia production, also for methanol production, which is used in the chemical industry, also in plastics, and it's also used in oil refining. So it's about 4 times the copper market by size. So multi-billion-dollar industry today, and 99% of that hydrogen is produced using fossil fuels. That is a highly carbon-intensive process, and it produces about 2.5% of global carbon emissions in the production of hydrogen itself. So that is significant on any measure. It's about equivalent to the aviation sector. And if you think about all of the activity and money being spent on sustainable aviation fuels and decarbonising the aviation sector, similar efforts are being put into the hydrogen industry, and that's not going away. So there is a need for green or clean hydrogen, regardless of where the market might find itself at the moment with the existing technology being electrolysis. And that's driving a lot of investment, which is continuing through this down cycle that we're seeing at the moment. And the investment is typically from either very large to very large in the town in terms of corporates, and large governments as well. So that money is effectively looking for homes, and we feel that new technology, as I said, is going to unlock the green hydrogen market, and we're hopeful that it is our technology that we're developing within Sparc Hydrogen. My strong belief is that if we can continue to progress the tech, then we'll continue to attract attention from the big end of town, and that will see the company really well positioned. We obviously have Fortescue already as a partner, but in terms of developing larger projects and getting the tech out to market, I'm really confident that the appetite is there. So just to touch on the challenges for the existing technology to produce green hydrogen. So traditionally, green hydrogen, as it's known today, is using green electricity via solar PV and wind to split water in an electrolyser. So that is a highly energy intensive process and uses a lot of green electricity. Now, the problem that this industry is facing fundamentally is that the cost of that electricity is too high to make the cost of the hydrogen that comes out the back end commercially viable. So that's the fundamental issue across all the projects in Australia and around the globe. There are other issues as well in terms of the infrastructure required. So not only solar and wind, but transmission lines in particular. These lines are very difficult to permit, and there's a high demand on the grid already for a decarbonisation of the existing electricity that we utilise in the economy today. And then there's also scaling issues with electrolysers. It's relatively new that these pieces of kit, although they've been around for about 100 years, have been talked about, for 100 megawatts, multi-gigawatt projects. And there's been some compatibility issues and scaling issues that the industry has found as it's been developed. And ultimately, electrolysers are still very high cost. So what we're doing within Sparc Hydrogen is focusing on a project called photocatalysis. So photocatalysis as opposed to electrolysis. Photocatalysis does the same thing. It splits water into hydrogen and oxygen without electricity. It uses the action of a specially designed photocatalyst material, and we utilise those photocatalyst materials in our novel photocatalytic water splitting reactors to produce hydrogen and oxygen. So sunlight is providing the energy. When that sunlight impedes on the photocatalyst material with water in contact, it automatically splits into hydrogen and oxygen. So it's a clean and green production method. It utilises simple infrastructure from the concentrated solar industry, and we feel that Sparc Hydrogen is the leading component in this field. We have a really strong partnership, and we just reinvested in terms of the commercial partners in January of this year into the project and the technology. So Sparc Technologies and Fortescue are equal shareholders of the joint venture at 36%, and the University of Adelaide holds a free carry 28% interest into the middle of next year. Their interest was earned through vending of the IP that exists within Sparc Hydrogen, exists within the project, and that was set out when the joint venture was initially set up at the beginning of 2022. So what we're doing within photocatalysis, which is an emerging but niche industry, is that we are utilising concentrated solar to effectively supercharge the photocatalytic water splitting reactor. So concentrated solar, for those that don't know, is effectively magnifying sunlight or concentrating it using mirrors. So we have a mirror system that we are utilising at our pilot plant, which I'll come to, which is effectively focusing solar radiation onto our water splitting reactor. There are multiple benefits from using this approach, including the fact that we need far less photocatalyst than if you were just laying it out in panels under ambient conditions, which is important. It allows us to integrate the technology into already modular and scalable concentrated solar fields, and we generate heat, and that heat drives higher efficiencies of the water splitting reaction, and it also means that there's a byproduct there in steam that we can potentially utilise and sell. Now, we believe the technology is unique and leading within this field. We had our first patent granted in January of this year. In terms of where we're at on scale up, so this project stemmed out of the University of Adelaide, and it was being developed there for a period of about 7 years before the joint venture got involved. So about 10 years go to woe. We're now at the stage of taking it out of the lab in a prototyping phase, which we conducted last year, into a pilot plant. So this is a significant step for Sparc Hydrogen and for the technology's development. We broke ground on that pilot earlier this week, so a really significant milestone. It's been located at the University of Adelaide's Roseworthy campus, which is about 50 kilometres north of Adelaide. And importantly, the pilot plant will utilise the infrastructure that we believe is scalable in a commercial fashion. So this is the type of concentrated solar field called a linear Fresnel mirror field that we're looking to scale beyond the pilot into larger and commercial deployments. So we're expecting the pilot plant to be built by the middle of the year, and we're expecting obviously a lot of data out of the pilot, but also a lot of de-risking of the technology, because we are effectively utilising commercial scale infrastructure with our technology, which has not been done before. So in terms of that modularity and what it can look like when scaled, this is a commercial linear Fresnel mirror field. It's in Spain. I've been there, and it's obviously a very large field. These mirrors at the bottom of the screen there on the right are 1 kilometre long into the screen, and then there are multiple rows side by side. So what we're doing in the pilot is taking individual modules of this type of mirror field, arranging them in a certain way, and utilising that to produce hydrogen using our photocatalytic water splitting process. If we can de-risk it to that level, we can then scale the mirror field end to end by adding modules end to end into a much larger setup like you see here today. So it really is significant in terms of moving to this pilot phase and what it does in terms of de-risking the technology. The other point about the tech is simplicity. So if I compare this process and this infrastructure to the competitor, which is electrolysis, for our system, we need a mirror field, effectively. That is the key piece of infrastructure that we require to produce green hydrogen. For an electrolysis plant, you need solar PV and wind. You need high voltage electricity infrastructure, which is expensive and difficult to permit. And you need electrolyzers, which are, again, expensive as well. So you've got 3 key pieces of infrastructure there versus 1. Now, the cost of any renewable energy project or most energy projects is in the cost of the infrastructure. So low infrastructure requirements drives the ability to have a low-cost system, which ultimately means low-cost green hydrogen. And why we're doing this and where we see the potential is because the demand for green hydrogen is not going away. At the top of this section, I discussed the existing use cases for hydrogen and the massive market that is there today. That's before you consider all the additional potential uses for clean and green hydrogen, whether that be for steel making or cement or a number of other hard-to-abate industries. So there's a massive interest and demand there. The key is, can you get a low-cost production system commercialised? And that's where we fit. And we don't believe the competitor, being electrolysis, is going to be at a commercial level for at least a decade, if not longer. And that provides a pretty substantial window of opportunity for new tech like ours to effectively undercut electrolysis and get into the market. And that's where we see the really strong potential around what we're doing. And I think that's where Fortescue sees a lot of potential as well. I will now jump onto our graphene business, and I'll skip through this relatively quickly, and please do ask questions at the end if needed. So within the graphene space, we are really focused in terms of our flagship product in one area, and that is the corrosion of steel. Now, it sounds simple, but it's a significant issue for global industry. It costs about $6 trillion per annum, and it costs a significant amount of greenhouse gas emissions as well. So corrosion means asset shutdowns, productivity losses, safety issues, and maintenance costs ultimately. So how the industry deals with corrosion, typically, if we're talking about steel, is through using protective coatings. So think paint, but these are specifically designed heavy-duty paints that are used on steel infrastructure. Now, that is a significant market. It's a $43 billion market estimated by the end of this decade, and it's covered by large global players who control about 50% of that market. So we are looking to develop an additive which improves the products that are existingly used in this market. And our view of the addressable market for the EcoSparc additive is about $1 billion US, and we believe we have the leading graphene-based additive relative to our competitors that can really crack into that market. So it's a significant opportunity, particularly for a company of the size of Sparc. So what is EcoSparc? It is a graphene-based additive. We are not a graphene producer, nor are we a paint company. What we do, and where our expertise lies, is in sourcing the right type of graphene and incorporating it into an additive that is suitable for that industry. So we have built a business and a company on the back of expertise from the coatings industry, and that expertise has developed this additive. It's a big differentiator from a number of other graphene companies out there, which produce graphene, and then they try and funnel it into different markets, including the coatings industry. There's been, I would say, limited success around that strategy because graphene is a very difficult material to handle. There are over 600 grades of graphene out there in the market. We've tested well over 100, and we only have a handful that work in our additive. So graphene is a very specific material, and you really need to understand it to develop it for an end use. And we've certainly done the work there in the anti-corrosive industry. So that's our key differentiator against a number of other graphene players. The other key differentiator and challenge that we've overcome is being able to incorporate graphene into a usable additive. So a lot of the industry, in terms of the graphene industry, will provide graphene in the form of powder, and they'll recommend a certain dosage rate for a certain application, whether it's in cement or coatings or other industries that are being targeted. Now, that's a very difficult proposition for an end user because graphene, as I said, is difficult to handle. And when you put it in a liquid like a coating, it wants to re-agglomerate into larger particles. So when we approached the coatings industry a few years ago, a lot of the industry was saying graphene doesn't work. And one of the key reasons they were saying that is because of this agglomeration issue. We've definitely overcome that and developed stable additives that stay well dispersed, as you see on the right-hand side, and you need a good dispersion to have performance benefits in this particular industry. And why I say that is because of how graphene is working, and we were the first company to really show this definitively, I feel, within the coatings industry. And it's working as a shock absorber effectively within the coating. Graphene is 200 times stronger than steel, along with being flexible and having a number of other wonderful properties. But within a coating, what we see is when a coating is put under stress, we see micro cracks. Those cracks propagate until the graphene particles, which are the black particles that you see on the right-hand side, and then they stop. So they're effectively acting as a shock absorber within the coating, and that is meaning less cracking. You only get corrosion where you have defects and cracking within a coating. So that is the key mechanism, we believe, why graphene and our graphene-based additive is improving the durability of these heavy-duty anti-corrosive coatings. Why should the industry care in terms of the end users? And the ultimate end users are the asset owners. So we've done a life cycle assessment, and we used an independent company to do that life cycle assessment. And we've modelled a significant return on investment through using an EcoSparc enhanced coating. So EcoSparc goes in the coating at a very low level, 2% within the coating. So it's not driving a significant increase in the cost of the overall coating, but it delivers a significant return on investment by extending the timeline between maintenance events. And we have 9 rounds of cyclic anti-corrosive data, which are typically 6-month tests that we've done in our labs here, which prove performance benefits anywhere between 26 and 79% for using EcoSparc in these coatings. We modeled 26% at the low end, and that delivered a 46 times return on investment for the asset owner. So really significant. If we look at the single asset that we modelled up in Queensland, almost $35 million of savings over the life of the asset, and a substantial amount of carbon emissions as well through using a simple additive to improve the performance of their coatings. So we've used that principle and that data to undertake field trials with major asset owners. And what we did there is used our commercially produced batch of EcoSparc. We delivered that to one of the global coatings majors, and they incorporated it into an anti-corrosive coating for us. So we have an EcoSparc enhanced coating, which is effectively the commercial standard coating with EcoSparc added into it under our direction. That coating is now being applied and used on assets around the country, including Streaky Bay on the Eyre Peninsula, Port Bonython, which is a Santos asset in the Upper Spencer Gulf, a mine site with 29 Metals in Western Australia, and more recently with BHP Mitsubishi Alliance at Goonyella. So these trials are really significant for a number of reasons, but they're de-risking the use of the EcoSparc additive in the eyes of the coatings industry. They're demonstrating strong market interest, which is important for our discussions with the coatings companies that we're engaged with. And ultimately, we're working towards inclusion of EcoSparc enhanced coatings on the specifications that these asset owners use when they specify what coatings can go on their assets. So that is a true demand pull through for the additive into the market. So the pathway to market for EcoSparc is dual track effectively. We're working with the asset owners, as I've just discussed, to get them the EcoSparc enhanced coating specified. And then we're also under testing and trials with 5 of the 8 largest global anti-corrosive companies in the market, along with a number of other smaller companies. Those trials are lab testing predominantly to demonstrate that the additive works in the products that those coatings companies have in the market today. So we're putting those 2 work streams together, and I'm really confident that 2025 will be a really significant year where we get commercialisation of the EcoSparc additive into products within the market that will ultimately generate revenue for Sparc. We're not just a one-trick pony in terms of graphene. We have ongoing R&D into other areas, and we recently received a grant from the Australian government, which was focused on using a graphene-enhanced material to limit anti-fouling or biofouling within the aquaculture industry. So that means the growth of marine organisms on aquaculture nets, which is a really significant industry and a really significant problem in terms of the biofouling. It has issues in terms of fish health, fish growth rates, maintenance costs, net replacement, and it's a really significant opportunity, which is why the grant was successful. We're also working in composites and bioplastics, where graphene can be used to increase strength, flexibility, ductility of, in particular, recycled plastics and bioplastics, which is a growing area in the market, as you can imagine. So just to touch on Sparc and where we have been over the last few months and where we're going, we've built a lot of momentum over the last, I would say, 3 to 6 months and ticked a lot of boxes, including getting the pilot plant underway and getting trials of EcoSparc enhanced coatings with global majors, including Santos and BHP Mitsubishi. So we're ticking a number of boxes there. We've also had our first patent granted for Sparc Hydrogen's reactor technology. What we've got coming up this year is really about delivery. So delivering the pilot plant by the middle of the year in terms of the Sparc Hydrogen pilot, which will generate a lot of market interest and data, which will then allow us to accelerate the commercialisation phase beyond that pilot plant. And on the EcoSparc side, we have ultimately field trials coming to culmination together with discussions with global coatings companies. And we're, as I said, really confident that we will get EcoSparc into the market during 2025. We've also got some grant funding submissions in as well across both sides of the business. And we have recent success as well with the federal government grant for the agriculture project. So a lot happening for the company, and I think we're really well positioned going into Q2 and beyond for 2025. So that's the end of the presentation, and happy to answer any questions today.
Thanks, Nick. Great presentation. So that concludes the presentation. If you have any questions, please type them into the chat now. I've already got a couple here. The first one is it viable that existing large area PV arrays can also be used as reflectors?
That's a good question. Not to my knowledge is the short answer. So for PV, which is effectively the panels that you use on your roof to generate electricity, the sunlight is coming in through a glass housing and effectively being utilised to excite electrons and produce electricity. Now, that same energy that is exciting those electrons is being utilised by our photocatalyst material. So we're utilising the same energy, and the reflectance of those panels is inherently low because they're trying to maximise the amount of sunlight that goes into the panel to do that process. Mirrors, obviously, we're relying on very high reflectance, so we want the maximum amount of reflectance such that we can focus the sunlight efficiently onto our photocatalytic receiver. And I encourage those interested to look at the video that we posted on LinkedIn and via our email distribution the other day, which really talked about the linear Fresnel system and how the sunlight is sort of coming into the receiver. So that's a really good opportunity to understand a bit more about the system.
All right, thanks, Nick. Obviously, recently there's just been an increased amount of skepticism around green hydrogen, both in Australia and globally. How do you think that affects Sparc going forward, I guess?
Yeah, it's a good question, and certainly we haven't been immune to the market, sentiment there. Ultimately, I see the shakeout of the green hydrogen industry as a positive. Hydrogen was well and truly overhyped, and electrolysis projects proliferated beyond what I think the industry was ready for. And ultimately, that's come home to roost when people have looked at the costs and looked at them closely and really understood that it's pretty hard to go from where the costs are today, which for electrolysis is, in Australia above $10 a kilo, to where the industry needs to get to, which is probably somewhere around $5 a kilo. Now, reducing electricity costs by 50% or more and reducing electrolyzer costs by a substantial amount as well is not a short-term issue that's going to be solved. So my interest in joining Sparc was not on the back of, hey, hydrogen's the best thing ever and, everything's going to succeed. It was on the back of Sparc had a differentiated position in the market, decoupled from the cost of electricity. And that ultimately, I think, can drive a step change in costs. And that, to me, is what is needed to unlock green hydrogen, unlock that 95 million tonne per annum opportunity that I spoke about, over a $200 billion US market today in terms of hydrogen production. Before you think about where the hydrogen is going to go in your car, I don't think that's going to be the case, by the way. Or in steel making, I think that will be the case. Or cement making. The opportunities beyond 95 million tonnes per year are quite significant, but you need a step change in the production costs to make that happen. And if Sparc Hydrogen is able to crack even a small fraction of that market, it's a multi-billion-dollar opportunity. And we have the leading sort of differentiated position there.
All right, thank you. Another one here. So obviously, if the Sparc hydrogen pilot plant delivers successful results, what are the key next steps and timelines after that? Will it lead to full-scale development or even a buyout from Fortescue?
Yeah. And so our recent announcement around the pilot plant construction listed out sort of over a dozen things that we were looking to achieve or are looking to achieve with the pilot plant. So as I said, we're looking to have that constructed and commissioned by the middle of the year, and it will play a significant role in de-risking the scale up of our reactor technology. So our reactor really is the key bit of smarts, where we're incorporating the sunlight with the photocatalyst materials and the water. So de-risking at the pilot plant level is significant, because to make bigger commercial fields, you're bolting individual modules together. That's sort of the simple way that I like to think of it. So I think if we're able to de-risk it at the pilot plant and continue to show that this technology and the advantages that it has in terms of its scalability, its flexibility, ultimately low cost when it's scaled, I think the opportunities beyond that for commercial deployment are really significant. And I think having a large scale end user of hydrogen, potentially in terms of Fortescue's green steel ambitions, along with a developer of hydrogen related projects, again, Fortescue within the JV, will play a really significant role around accelerating deployment into the market. And we know that Fortescue, when they put their mind to something, can really deliver things quickly. So they can add a substantial amount to the joint venture and actually bringing it from a state of technology development to commercialization, I believe.
All right, I think there's I'll come back to a few other questions, but one just sort of came through that follows on from that. Is the future of Sparc Hydrogen to manufacture or license the water splitting technology? How will the company make its money?
Yeah, it's a really good question. So Sparc Hydrogen is a technology company. It's a technology developer. It's not set up as a project developer. And certainly the goal at this stage is not to do that either. So how do we commercialize the technology? Ultimately, we need to prove the technology to a certain scale, such that it de-risks it to a point where other end users of hydrogen are willing to deploy it for their own use cases. So I think the pilot plant is a major step, as I've just described, towards doing that. And there's probably a larger deployment beyond that, at that commercial scale, which can be done beyond the pilot as well. How we make money out of it is through the technology, licensing the technology, and taking, potentially small stake in projects. So it's a number of ways you can monetize once you've developed the tech to a point where people are willing to deploy it at large scale. But the short answer is Sparc Hydrogen is a technology company, not a project developer. It has a capital light approach to things, a capital light model, and that will continue.
All right, thanks, Nick. That probably covers a few of the questions that have come through. I'm just going to put two together here that are sort of a bit technical. So what's the durability of the catalysts, and is water purity a factor, and what happens to the leftover, I suppose?
Yeah, good question. I'll start on durability. So photocatalysis has been known about in terms of water splitting for about 50 years, but there's been substantial effort and improvements to photocatalyst material over the last 5 years for obvious reasons, given the advent of green hydrogen. But what we've seen in terms of the improvement is in the efficiency of the photocatalysts in terms of how efficient they are at splitting water, and also their durability. So one of our collaborators is Shinsu University in Japan, and we're public on that collaboration. And they have shown durability of photocatalysts in the field now over a substantial period of time. So they have panel systems that they've had deployed for a couple of years with their photocatalyst materials in them. So that's a really good demonstration of the durability of the catalyst materials that we're looking to use. Obviously, we're doing that under concentrated sunlight. So one of the things that we are looking to understand is, in a field environment, does that durability stand up to the conditions that we have within our reactor? So we'll be able to show that for the materials that we're using. And then we're also looking to test different materials. We have collaborations with other groups around the globe developing these materials. And ultimately, we want this pilot plant to be a bit of a calling card for those collaborators to say, well, we've got a facility which is the first of its kind globally that can test your catalysts under concentrated sunlight. So come and do it with us and our facility. So that's the answer to the first question there. The second question, or second part of that question, Simon, just remind me.
Is water purity a factor?
Water purity, yeah.
And what happens to the water?
Good question again. Yes, so the type of water that we are feeding into our reactor is equivalent to what you'd feed into an electrolyzer, so high purity demineralized water. We have not tried some significantly lower grades of water at this point in time. Will we in future? Yes, likely we will. Do I think that high quality water will be required? Yes, I do, because these photocatalyst materials are ultimately semiconductors. You don't want impurities depositing or deactivating the photocatalyst material. And for the extra cost of that high purity water, it makes absolutely no difference to the overall cost of the project. So you're better off using the highest quality water possible.
All right, thank you. That probably covers Sparc Hydrogen. There's a couple on EcoSpark, and I think you've probably answered this, but just remind everyone when you expect the reports to be back on the test for EcoSpark.
So in terms of the field trials, we're expecting the first of those towards the end of Q1, and the first being one of the assets in Western Australia with 29 metals, and second being the Streaky Bay Jetty, early Q2. So we're going to have field trial results in terms of the initial inspections in the next month or so. That initial inspection is really important because early failure of these coatings is typically by delamination, cracking, poor adhesion, blistering, and those types of failures typically show up within 6 months. So if we can show that the coating is not showing signals or signs of those early failure mechanisms, it goes a long way to de-risk the application of the coating in the field. The longer term data around corrosion, yes, it will become evident during the trials, but the industry really relies on the lab data that we do to the ISO standards here, and that the coatings companies are also doing themselves. So we're looking to pair the real world data, the early phases of the field trials, with the lab data that we've generated and that our collaborators have generated, who are ultimately the customers of the additive. And that's why I say that, by within 2025, I think we'll be really strong in position to get EcoSpark commercialised, likely in the second half.
Very good. I think we've probably just got one more. Just about the anti-foul coating. How big is that opportunity, do you think? I know it's only sort of not your priority, but I guess.
Good question, and it's a really interesting area. We've been looking at anti-fouling with Flinders University. We've had an active project which we've leveraged for this recent grant for a couple of years now. Anti-fouling is a massive industry in terms of anti-fouling coatings. So these go on the bottom of ship hulls to avoid barnacles, seagrasses, etc. growing on. And they're so important because if you have that type of material growing on your ship hull, the increased drag, which leads to increased fuel use, is really significant. So all shipping companies, all ships, boats, even leisure craft use anti-fouling coatings to reduce and eliminate, in some cases, the growth of those species on the bottom of those hulls. What we're looking to do with our graphene enhanced materials is to deliver anti-fouling performance in a much more sustainable and hopefully lower cost way, in terms of lower cost coatings for ship hulls and also lower cost materials that are utilised in the aquaculture industry to reduce the growth of those particular species. So the tech we're developing is utilising one of graphene's key properties, not the strength and flexibility, but one of the other key properties in quite a novel way, ultimately developing the tech, patenting it, and then leveraging that to make money is the approach there for Sparc. And I think the opportunity there is quite significant because it's quite novel in terms of what we're doing, and there's limited other good solutions that are available in the market. To give you an example, the existing coatings used on the bottom of ships basically leach copper into the ocean. Number one, they're really expensive coatings. Number two, they need to be replaced quite frequently because they're designed to degrade. And number three, the environmental impacts are quite significant. So, you don't want to go swimming in a port because it's full of biocidal material, effectively.
All right, thanks, Nick. That's the last of the questions. Very good. Thanks everyone for joining.
Thanks, Simon. Thanks everyone for joining.